All right. So I was gonna spend one, or I was actually gonna go straight into looking at different parse trees, which is where we need to go. But I realized that we need to spend one more session sort of wrapping things up for when you see the actual code base that you need to work on so that you'll sort of understand why it is the way it is. So, there are a couple of important things that I've left out so far. Um, the biggest one, the biggest one is this, and again, you'll see this eventually, but not yet. Um, the biggest one is this. Okay, so let's say la 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 la. Let's import this.
Should we be looking at?
Oh, sorry. Sorry. One second. Whoopsie. Okay, can everybody see my screen?
Yes.
Okay, cool. So the biggest thing that I haven't talked about yet was the following. So here, I just imported Quill, and now let's say I'm going to make a tree. And then let's say p2p.name equal to Joe, right? We've seen this 100 times by now. Oh, right. I have to import the context. Create it. Oops. We've seen this query a bunch of times already. Let's look at the syntax tree. Here's the syntax tree. Now, here's the thing, right? We created this query right here where we said, okay, ident of p. Right, so here's our p, right? And we're filtering on p.name. Okay, great. Well, here's ident of p. Okay. What the heck is the type? What is the type of this thing? Right? Is it an integer? Is it a class? What is it? What is the type of this thing? Well, we don't really know. It's not really telling us. We don't know what the type of this thing, we just know that it's some kind of identifier. Okay? Well, what about this entity here that we've defined? What type is this? Well, it's sort of a person object as we defined here, but what are the fields of that thing? Well, again, we don't really know. So this is a syntax tree that is not typed. Which is fine. You can have syntax trees that aren't typed. But in the latest version of Quill, and the version that you're eventually going to be working with, there are types on everything. So let's look at potentially an example of what that looks like. Let's look at this one. La 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 la. blah, seen this 100 times. Now, okay. Let's change the way that this is printed. System.setProperty Quill dot one second. What's this parameter called? Quill dot quad dot show. Oh, 1 second. Let me just check what the parameter of this thing is. Oh, trace.quat. Quill dot trace dot quat. Let's see if it will show it this now. Oh, print. Quill dot util dot q print. And let's say the q.ast. What? Oh, util dot messages. There we go. Okay. Well, now, as you can see, there are these funny little things inside of everything. This ID is the same as ident. I just print it more shortly. In fact, what happens if we just do this now? Okay, no, same thing. Okay. So let's compare. What did we have before? Let's compare this with this. Nope, I mean this. La 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 la. Okay, sorry, I need to make this an apples to apples comparison. La la. Let's do ID. They're the same thing, but I'm just making them look the same because they're printed slightly differently because these are two different versions of Quill that have introduced some radical changes. So here is what our query is. Here is what the tree used to be. Here is what the tree is now. Notice that we have these things, these funny looking CC things here. So what this is this is actually the type. Right? Where's our definition of person? Person is name and age. Right now it's just V for value. So we have three now, but two basic things. We have this notion of case class, or a product type, and the fields inside, and their corresponding value. Now, of course, we can have multiple things inside of each other. For example, if we choose to do something like this, first string, last string extends, embedded, and then we do something like case class person first name, and then, we do something like that, and then we print it. Well, let's see what... let's see, did I redefine person? Oh, whoops, I forgot to redefine person. Oops. Oh, oopsie. Just made a mistake. Base class name. Base class person. Val Q. Ah, now name.first equal to Joe. Voila. So now, since we defined a name type, that's actually a case class inside of a case class. So now the type is more complex. Let's have a look at this. So what this introduces is a notion of typing. There is, let's just copy and paste this down below. There is this type called person that has a type name that has a first and a last field. So now we have embedded fields. And also now, now instead of p.name, it's going to be p.name.first. So it's going to be a property inside of a property, right? The outer property is first, the inner property is name, right? That's how this gets translated. And of course, the inner property, the inner type of this thing is this nested type, right? Because name is now not a value like it is over here, right? Name's value here, and here it's an embedded kind of object. So this is, you can think of it like JSON, sort of, but it's basically a embedded type system that now exists in the syntax tree. Now, the second that you introduce this kind of embedded type system, you have to parse the types to create the type system. So for example, if you look at, let's have a look at some new, or let's say newer Quill code in Scala 2. Let's have a look at entity, AST. Or let's just look at let's look at entity. Here's entity, right? It has a name. It has properties or renames like we've seen before, but now it has this thingy here called quat. Quat means Quill application type. So this thing has a actual type on it. So when we create this thing inside the parser, and look at that. In our query clause, we create an entity. And in addition to the list of properties, we actually need to infer the type of this thing. So we take the type that's available from this parameter here, which we've parsed, and we actually have to go through this long process of inferring what this type is. So what this does is it converts this thing here, this variable t, which is a Scala tree type. Remember how back when we were looking at these crazy type trees inside of Dotty code, where this was, we had these trees inside of these trees, right? And most of it was not really relevant. right? So what this thing does is this thing parses the actual type tree and produces this thingy right here. So you're not going to see it yet, but eventually what you're going to see is you're going to see something like this in the code, in the Dotty Quill code. Again, I will be taking care of this part. Like, there's a big pipeline in here that's actually supposed to parse the types, that goes through different kinds of types and parses them and understands all sorts of weird things about how the Scala type system internally works, blah, 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 blah. You won't have to deal with this, but you will have to know when you have to invoke this function. Right. Same thing when you're trying to create an identity. Sorry, an identifier, right? Here is an identifier. So we create this ident thingy, right? And again, you have to actually look at the type and figure out what the quat is. Again, quat is Quill application type. Now, in order to create this Quill application type, in Quill, there needs to be an internal type DSL, or an internal type AST, right? So just like we have the AST for expressions, which is blah, 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 right? This thing here, right? That's the AST for expressions. We have an AST for types, which is a secondary AST embedded with the primary AST. So there's type.product, which is this case class thingy here. And again, the infer quat thingy, this thing here actually instantiates something of this type quat. Like, the root level type is called quat. And it has product, which is this CC thing, product or case class. I use them interchangeably, which has a list of fields. That's where this linked hash map comes from, and a bunch of other stuff. This is something to understand. Sort of, you can create a syntax tree that's typed. You can create a syntax tree that's not typed. If you're creating a syntax tree that's typed, you actually need to have an embedded type system. The reason that I created this thing was the following. When you have something like this, and when basically your command is tokenize, right? And basically what you have to do is take something like this. Let's say you just have that, and you have to make a select statement. Let's say tokenize ident of p, right? You need to make a select statement. Let's say you already know everything else that's supposed to go into the query. You just have to make a select statement. What can you do? Well, you could do that. But there's not much else you can do besides for that.
Hey.
Hey, what's up?
I didn't know we were meeting today.
Oh yeah, sorry. Yes, I need to wrap up with a couple of things. I'm talking about this additional thing that that you're going to have to deal with called types or quats. And again, I will mostly do this work, but you'll have to call. I just introduced this function here called infer quat that you'll call to create this type. And the point is that the trees, so far we've been dealing with syntax trees that just represent elements. Like, there's this ident, ID is ident, same thing. There's this ident of p, but what's the type? Right? Is it a string? Is it a Boolean? So newer versions of Quill introduce this notion of quat or Quill application type. So here we know the type of this thing, which is a product or case class that has two fields, name and age. right? And so we actually have defined person as this, right? So that's the quat. This is actually like, I don't put the name here because this is not.
Wait, what'd you call it? The quad?
Yes, it's called a quat. It's
A quat.
Quill application type.
Oh, okay.
There we go, quat. This is the root level. And basically, in the parser, parser, in order to figure this out, right, before we just could create an ident, right, before we could just do something like that, right, and then we were done, or something like that. But now, essentially, there's this other thing where you need to know the quat. And so there's this function here that I created that will create the quat. And it does that by going through this long pipeline here that parses the Scala type and understands it. So that's basically that's the first thing to keep in mind, that we are dealing with type trees. And the reason why is let's say that you're
I'll be right back.
All right, sure. Let's say that you're expanding this expression. Right? You don't know anything inside of it. Like if you want, let's say, you're given the select clause, you're trying to expand an identifier. What can you do? You can do dot star. But you really don't know much else about it. Like you don't know what fields you need to expand to. As opposed to if you have, right, then you know that, oh, okay, I have this name field. I have this age field. Right? You actually know, okay, you're supposed to expand to p.name, p.age. Now, of course, we were able to do this before quats, but it was a very, very different and difficult, convoluted process. The reason why quats were introduced is for these kinds of expansions to be simpler. So, this is sort of, long story short, this is why we have a notion of quats. This is something to keep in mind. Again, you will not have to write this infer quat yourself. I will write this, but you'll have to use it and pass the Scala type inside. And when you're creating things like identifiers and entities and other things, you'll have to use it to actually create the type. So this is the first part to watch out for. Now, the second thing that I wanted to talk about was when you actually look at the real lifter and unlifter, you'll see all of these implicit things. You'll see all of these implicit things, and what they are is type classes that I've used to help with the actual lifting and unlifting. Here's why. Let's see how we got to this. This is also sort of important to understand. Right now, we have this basic unlifter. Let's look at what is this? This is the lifter. Let's look at the lifter first. Okay, so we have all of this stuff here. We have the supply function, and it calls the lifter on stuff recursively, and then potentially when we need to do things like lifting.
I'm back.
Okay, cool.
Sorry.
No problem. We're recording, I hope.
Yeah.
Anyway, so we have lifting stuff. We have a way to lift stuff. But as the amount of stuff you need to lift and unlift grows and grows and grows, and some of these expressions grow and grow and grow, you start having issues. So, for example, let's say that we have this alias, which is this identifier. And we kind of have a way of lifting all identifiers, but we sort of recursively apply this whole thing, and then we have to do this ugly cast. Or we have to explicitly call this lift on a binary operator. There are all sorts of situations that we encounter. Oh, and by the way, we've mixed kind of, different kinds of parsing of binary operators. Eventually, what we want to do is we want to be more flexible. Oh, and by the way, this other issue, right? Constant, right? So we are parsing constant has a value. Right now, we've only considered strings. Obviously, constants can have ints and longs and booleans and other things as well. So, for example, let me just check something. Right. What ends up happening is that we want to have the ability to do things in a more flexible way. Oh, here's name, right? Property has name, which is always going to be a string. Right? Maybe we want to be more flexible about how we handle that. So eventually we want to have some kind of more flexible system that we're able to add components to that are a little bit modular. So the way that essentially what we want, let's say that we're trying to parse a property, right? We're trying to parse a property. And what we want is we want to lift the name. Well, what we want is to have some kind of way to lift this. Or let's say we're in filter and we're parsing this alias, right? So, okay, we're recursing on the thing inside, which is actually a lift of AST, and we don't really necessarily even know what'll come out of this thing, which means we have to cast it, which means that if we screw up here, then this throws a class cast exception, right? So we want this to be a little better, right? Ideally, what we want to do is we want to be able to do something like something dot get lifter of, let's say, ident, and then apply it on this alias, or something like that. Now, again, the way that this would be done in Java is that you would have some kind of big hash table that would be storing all of your lifts, which is also not entirely ideal, because whenever you do something like that, you actually don't know if your hash table has a lifter for some type or not. So in order to get this kind of thing, the fundamental problem that we need to have is we need to have some kind of conversion between a type, say ident, and a lifter that lifts idents. And we actually want an instance that lifts idents, right? And we want to have some kind of mechanism to do this. Well, how in Scala do you create a mechanism for translating a type, this, into a term, this? Well, typeclasses. So, How do you implement type classes? Well, the way that you implement type classes in Scala 2, we're going to use the Scala 2 model. Eventually, we'll transition into the Scala 3 model. But in the Scala 2 model, what you have is you have something like this. You say, let's say, define ident lifter. Okay? Ident lifter. Okay, we have this object lifter. Okay, so we need to have different kinds of lifters. We need to have different kinds of lifters. So, trait lifter of some type T. Okay. What is a lifter of type T? A lifter of type T is going to be something that has this method called lift. And this method called lift has the capability of taking some kind of T and then returning an expression of T. So that's what lifter is. So now, what we could do is we could say, okay, let's define a lifter of identifiers. Which is going to be a lifter of ident, and then we actually have to create it. Okay, let's make one and define this lift function, which takes ident. Right, this was the type signature that we had here. So now we're actually instantiating one. Okay, so let's instantiate it. Lift of ident that returns an expression of ident. What is that? What is an ident lifter? Well, it's just this thing here. Right? That's our ident lifter. Okay. Well, let's just use this entire expression. Ident. Sorry, it's going to be element of ident. Element match. Voila. So now we have an ident lifter. Okay, well, what does that help us with? Right, well, we could just call him right here. Ident lifter.lift. We could just call him. Okay. We could call ident lifter.lift. And then we wouldn't need to have that. Well, that's kind of nice. Can we do better? What is this? Whoops. Can we do better? Okay. How about this? Let's say, for example, that we have an implicit class and we'll call it hasLifter. That implicit class depends on another implicit. It depends on the idea that we have an implicit ident lifter, or sorry, that we have a implicit lifter on what type? How about on T? There is a implicit lifter on some type. What does this mean? Given there is a lifter on T, therefore, there is a has lifter class on T. Okay? What can we do with that? We can define methods on it. How about defining a method called lift that doesn't even need to take any arguments? If we have this lifter on T, we can define this lift on T. Okay, we can define this. Oh, by the way, has lifter, we actually have to define what the heck this is on. Okay, here's our element, and guess what? We have this thing, and we know that we can do lifter.lift and pass our element inside. Okay, well, what does that give us? Well, here's what it gives us. Here's what it gives us. Let's change the supply function. Let's change the supply function. And actually, no, we're fine. We don't need to change that yet. We don't need to change that yet. Let's say that, okay, we've defined a lifter on type T. We've defined a lifter on type T, and then we've defined an ident lifter, which is a lifter of a type. Okay? Well, now, instead of alias dot lift. Ooh, what is alias? Alias is an ident. It has a lift function. The lift function is defined here, which relies on the existence of a lifter, which we have just implemented here. Can we do this for anything else? Well, actually, well, first of all, let's see. Okay, no. We don't have anything else that would use that for now. Let's see. Can we use the same kind of approach on this binary operation that we had to write this function for up here? Oh, this is the exact same signature as a lifter. So how about this? Binary operation lifter. It's an implicit. And then we define, instead of this being here, this is a implicit lifter of a binary operator. Okay, new lifter of binary operator. Okay. Oh, and of course, it needs to have an actual lift function, right? This is our lift function. Def lift, our element, is a binary operator. It returns an expression of binary operator. Okay, so it's well typed. Like the typing behavior is spot on. So you don't have to do any casting when you use this pattern. Okay. So let's see. It's complaining about indentation, but we don't care yet. Now lift. We have an element expr of that. And are we missing anything? Oh, yeah. Right, that's probably going to have that. Oh, and it's not element, we'll call it op because we've called it op in the rest of the function. So now, la 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 la, all we have to do is say binary op dot lift. Okay. Well, that's simple enough. Let's just shove that into there. Okay. So now we're starting to see this sort of pattern emerge where what we could do is we could use these type classes in order to be able to abstract away parts of this system. And, oh, by the way, on the root level, what do we have? On the root level, we have an implicit def AST lifter, which is a lifter of AST. Now, wait a minute. This is AST, but identifiers are subclasses of AST. How do you know whether you would hit this or that when you would try to lift something? We are not using type trees to lift. That's not how lifting works. You don't, in order to, that's not how case classes work. Case classes do not work according to the type tree. It's called invariance. They're invariant, right? Like when you have a list of animal and you try and cast a list of cat to a list of animal. Sometimes it works, sometimes it doesn't. Depends on your language and also depends on your type system. So when it does work, that's called covariance. When it doesn't work, it's called invariance. There's also something called contravariance, which is similar, but I don't want to go into that now. The point is that lifters do not follow the type tree. They are invariant, which means that when you say .lift, an alias is ident, it uses the ident lifter. It doesn't look down the class hierarchy to figure out what it's supposed to be. No, it just says, do we have a lifter of this exact type? So implicits are invariant, and this is important to remember when you're working with stuff like that. Anyway, so we have this top level AST lifter, new lifter of AST. Ooh, okay. Okay. Def lift. And it has an element, which is an AST, produces an expression of AST, and, let's just call it AST, and la. Yoink! Oh, and our apply function is just, our apply function, in this case actually AST lifter, I'll explain to you why this thing is implicit. Here we just do AST lifter of AST, okay. Fine. Method AST lifter and object lifter does not take parameters. Right, excuse me. Not lift. Ah. Oh, but wait a minute. We defined a has lift on AST. And this lift attaches a method called lift, which means what we could just do is that. Okay. Right, now this is getting interesting. Which means that instead of that, we could just do that. Instead of that, we could just do that. La la la. Okay, let's splice that in there. Let's take that, splice that in there. La la la. There we go. Okay, right? This is getting interesting. Oh, and also, let's see, ident. Oh, is this an, no, this is another AST. This is actually, we'll call it inner because it's not necessarily an identifier. But anyway, la 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 la, left. Okay. What about constants? What about things like string? What about things like string? Implicit def string lifter of string equals to new lifter of string, and okay, def lift str string becomes an expression of string, okay, which is just expr of str. And now we can do name.lift. Ooh, this is query dot lift body dot lift name, which is a string dot lift. Ooh. Okay. What about a constant that takes a value? Now let's let's leave that. Let's leave that. That's a more advanced case. Let's leave that. That's a more advanced case. Let's see. What is this defined as? No, let's leave that for now. So anyhow, so this is right. This is a useful kind of pattern. This is a useful kind of pattern when the amount of things that you have to lift becomes bigger and bigger and bigger. Oh, look at that. Entity. Ooh, entity has a list of associated properties. How do we lift that? How do we lift a list? Well, can we implement a list lifter? What's a list lifter? What's that? Well, it's a lifter of a list, but it's a list of some type. Okay. Okay, new lifter of list of t. Okay. A def lift of of list of t is an expression of list of t Ooh, what do we do with this? What do we do with this? Well, we need to be able to lift the list somehow. Oh, there's expr.ofList. Well, that kind of works. Okay. And so we can lift a what? We can lift a sequence of expressions of t. So we need to pass some expression of t. Ooh, but do we have t? Do we have expression of t? No, 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 no. We have t, right? We're going to be calling list lifter on what? On a list of string, not on a list of expression of string. But that's kind of problematic, because in here, we need a list of expressions, right? This kind of makes sense, right? What this is telling us is if you have a list of expressions of t, then we can give you an expression of a listed lift of them. So in other words, it's telling us if you have a list of honey jars, we can take that list of honey jars and we can pack it into a crate, right? Right? So we could say list of crate of honey jar, jar of honey. What we can do is we can pack that into a crate of this, we can pack that, sorry, I'm confusing myself. If we have a list of jars of honey, we can take that list of jars of honey and we can pack it into a crate. Oh, let's unify our metaphors. Instead of jar and crate, let's call it container. If we have a list of honey containers, we can produce a container that contains the full list, right? Because if our honey is in a bunch of containers, we can put it into one big container. Right? That kind of makes sense. This is similar. There are many, many similarities, but this is like a very common principle that you'll see in many, many, many areas, right? If you have a list of something, of some container that contains something, you can then create a container that contains that list of something. This is actually also very similar to if you're doing like future, if you're dealing with like future or a promise, you'll be like a future. Let's say you have a future of, let's say it'll give you a glob of honey. And let's say you have a list of futures of honey. What you could do is you could create a future/promise of a list of honey globs, right? Because what does it mean, a future of a glob of honey? It means at some point in time, you will get a glob of honey. What does it mean to have a list of those? Well, it means at some point we will get all of our globs, or we'll have an error. Which means what we can do is we can say, okay, wait for all of them. Right? When we're done, then give them all back to the client. Right? So this would be like future.sequence or something like this, or get all. Right? And then you would pass something that is a list of future of honey. Right? And this would return to you a future of list of honey. So this is a super common pattern. So if we have a list of expressions, you can think of, again, an expression is like a cocoon, right? If we have a list of cocoons of something, like of some tea, if we have a list of cocoons, we could take all of our teas out of our cocoons and put it into one big cocoon. Okay? But what we have passing in, what we need to be able to pass in, is not a list of cocoons, but a list of the things inside. Right? We have a list of larvae, not a list of cocoons. So we need to cocoonify all the larvas first. Well, how do we know we can do that? How do we know we have a lifter or cocoonifier of our tea larvas? How do we know we can do that? This is where the Scala type system becomes scary good. Implicit T lifter or element lifter of T. In other words, given you have a lifter of T, therefore, we can give you a lifter of list of T. And T is an arbitrary type. And T is an arbitrary type. They call it gamma. Like we in terms of values, like 2 or 4 or 3 or 5, we call it X or Y or K or whatever thing we want to use. But a variable that represents an arbitrary type we call gamma. So we have a list of an arbitrary type. And we have a lifter for that list of an arbitrary type. Which means that we can then do the following. We can then say, all right, list of lifts, and we could say list.map for each element lifter.lift of E, okay? Right? We all should know how map functions work by now, right? Especially since they're like in every language now. There we go. Oh, this has to be, is this gonna work? Expert.list. List of expertise, expert.list. Found expert of list of T expert. Wait, did I do? Oh, wait. Oops. This type signature is wrong. It's supposed to be expert of list. Sorry. My bad. So there we go. Right? We can produce a list of expressions or a list of cocoons because we have a element cocoonifier, and then we can pass that to cocoonify them all. Which means that, okay, so now how do we cocoonify this? Oh, an entity has two things. At least for now. Eventually it'll have a quat, but right now it has two things. This other thing is a property alias. What's a property alias? Let's look at what a property alias is. Property alias. What is that? What is the type of a property alias? It's a list of property aliases. What is a property alias? Property alias. Okay. It's just a class that has a list of paths and an alias. Implicit def. Property alias. Lifter, which is a lifter of property alias, which is a new lifter of property alias. Okay. Def lift of list, or excuse me, lift of alias, which is a property alias, which gives you an expression of property alias, which is following. Right, just like we have our syntax here, quote, property alias, right? We're splicing code now. Property alias. Ooh, let's just match it. That's the pattern we've been using. Right, we could just do, right, at this point, we have two things. We have this list here we don't know what to do with yet, and we have this alias, so let's just put null here, but at least let's put this because we know that exists, right? We could do at this point, we could just do alias.lift, right? We know we have a string lifter. Sorry, alias dot, what's the value? Oh, alias.alias. Okay, let's call this property alias. Property alias. Property alias.alias.lift. Right? We could just do that. That's fine, right? The pattern that I used was that I just said property alias match, which is actually less efficient, but it looks prettier, whatever. Again, the efficiency is not really material in this particular use case, so I just do it like this. Paths alias. And then I just do that. Property alias. Again, we don't know what to do with the list yet. We can splice the alias. Right? Or, excuse me, lift. And again, because alias is a string, and we have a tokenizer, or excuse me, we have a lifter of string, which again means that we have a implicit has lifter on it, which comes from the string lifter, so we just do dot lift on it. Ooh, but what about paths? Paths is a list of string. But wait a minute. We have a list lifter, and provided that we have an element lifter of t, we can summon a list lifter. So what happens if we just do paths.lift? Let's see. What happens? Int to option of string. Required list of string. Found int to option. Required quoted expression of string. Why is this? Where's this coming from? Okay, no. Our compilers, our IDE is being dumb. This should work. Yeah. In fact, what we could even do is this. Right, we could explicitly do that. La 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 string. Does this work? What happened here? Found paths, list of string required. Oh, whoops, lifter of string. Dot lift. Excuse me. There we go. That'll work. That'll work. So yeah, so all we have to do here is dot lift. Let's actually, before we go any further, let's compile. Let's compile and just be sure that our code works. Compile. Compiling. Oh, wait, what did we do here? Why is this failing on us? Required expression of list of string found int to option of string. Okay, where is this coming from? And that seems to work happily. What's the problem there? Oh, that, it doesn't like that. No, nope. Oh yes, one other thing that we need, this is a type. The type of key needs to be known. Okay, there we go. And what's the problem now? Cannot lift the tree ident of P. And what are we missing? Yes, and so now we've refactored out all of these. We have a ident lifter. And now we still have to, in our main thing, we have to include ident. And we can just do ID, ident, and we can do ID dot lift. And that's fine. Okay. I don't know why it has this issue. I don't know why this, oh, wait a minute. Does list actually have a method? Does list actually have a method called lift? Let's see. Let's just look in our code. val v equals list 1, 2, 3 v dot lift. Okay, that's why. That's why. There is actually a method called lift that's defined on a string object. And I didn't know that. And so when you're creating a method, that's overridden on some kind of lifter object, then you can't override a method that actually exists on a lift. Wonder what that is. Let's see, Dotty doc. Let's see. Is there... Wait, hold on, no. Let's see what's on lift. What's lift on the list? Lift. Turns this partial function into a plain function, returning an option result. What? A function that takes an argument sum this of x, if this is defined. Turns this partial... What the heck is this? Turns this partial function into a plain function, returning an option result? Function that takes an argument x to sum dot this dot x. Oh, wait. I think I know what this is. List 1, 2, 3. Let's say foo bar lift 3. None lift 1. Okay. See what this means? This is a function that says, give me an index. If that index exists, then I will return to you an optional of the element of that index. Otherwise, give me nothing. It's basically the equivalent, let's say val L equals to list of foo bar, right? What you could do is you could do L dot get 0. Let's say L dot get 1. Okay, no, that doesn't work. Get is not a member of list. Okay, so that doesn't exist. You could do L dot apply of index 1, or L of 1, which is the same thing. Fine. Or of 2. Index out of bounds exception, right? Because our list only has 2 things, foo and bar. But there's no dot get. It's just dot apply. However, what if you want the following? What if you want to do something like L dot, let's say, L dot get or optional, right? Like you want to do something like L dot get the third index and then match case exists or some value. Yay! Value at index 3 is value. Case none. Nope, we don't have anything. Okay. Oops. Syntax. Well, except for the fact that there's no such thing as get. And it doesn't return an optional value. Right? You could do like get or null, maybe. And then maybe it'll give you a null, but there's no such method either. So what do we do? It's called lift. So it'll give you, nope, we didn't have anything. How about it, index 2? Nope, we don't have anything. How about at index 1? Ah, that's bar. Okay, so that's what lift is on a list. And so because what we tried to do here, is we tried to override the lift method inside of our implicit class, it said, nope, no can do. You cannot do .lift on a list. And then we tried all sorts of other things, like we thought, okay, summon, maybe this thing has lifter can't be summoned on a T. So we tried has lifter of string, right? And then we're like, okay, does that exist? And it's like, nope, doesn't exist. Actually, you can't do that. That's not a valid statement in the first place. Right? We tried ident, and it didn't work either. And we definitely know that one of these things existed for ident. Right? Because it's not giving us a compile error. Otherwise, it would have given us a compile error right here where we try to lift ident. Right? Like right here. Da-da-da-da, da-da-da-da, right? We're good there. So anyhow, so you've just witnessed how you debug issues with implicits, which is very much trial and error. You just try random crap until something works, unfortunately. So anyhow, so let's just do lift A, or change the name lift to something else. But anyhow, back to our previously scheduled program. The point of all of this was the following. We can define a lifter on type T, on some arbitrary type T, and if there is a lifter on that arbitrary type T, then what we can do with that is we can then say, if there exists a lift of stuff, then we can lift that list of stuff, provided that for every single stuff-ite, we have a lifter for that stuff-ite. Right? Or, in other words, if you have a list of larvae, if you have a function that cocoonifies a single larva, you can then cocoonify all of them and put them into one big cocoon. So that's what this list lifter is. So if we have a lifter for an element, we can then define a lifter for them all. And this is a super common pattern. For example, let's say that you're doing something like encoding JSON, right? Let's say that we want to have, let's say, trait encoder. Let's say JSON encoder of T. Then you have def encode T of type T, or let's say element of type T. And that will yield an expression, or excuse me, that'll yield a string, because this is a JSON, right? If we have a JSON encoder, okay, let's define implicit def string encoder, which is a encoder, JSON encoder of type string. What is that going to be? That's going to be new JSON encoder of type string. Okay. Def encode lem, which is going to be a string. Okay. Right, so that's pretty darn easy. Just add a quotation. Just add a quotation to it, right? And let's say we define an int encoder. And then we could do JSON encoder of int. The element is an int. And now we can do, and that's just going to be the element plus that. That's how you do that. Okay, right, and we could call this int encode on 3. Oops. Dot encode. Right, or we could call string encoder dot encode on hello. But now we could do something more powerful. We could say def list encoder, which is define an arbitrary type or a gamma. Implicitly, given that there exists an encoder, an element encoder of, which is, or by the way, which is going to be an encoder of type T, then we can produce for you a list encoder of type list of type T def encode, which has a list of T, and again, just map it, element encoder, take the element encoder, encode every single individual element, right? Because we have an encoder on T, so we can encode every single individual one. Okay? Okay? It's not encoder, JSON encoder. JSON. What? JSON encoder. Wait. Encoder. Not found. Type JSON encoder. What? Did I spell it wrong? JSON encoder. JSON encoder, JSON encoder, JSON encoder. What do you mean the type is not found? Oh. Okay, that doesn't look right. 1 second. No, that's fine. Does not take parameters. Element. Oh, whoops. My bad. Element encoder dot encode. Oh, sorry, not encoder, dot encode. And what else did I do wrong? Oh, encoder. Encoder. Excuse me. Encoder. Spelling mistakes. And what else did I do wrong? Element. Dot encode. List.map. Oh, right. Excuse me. So okay. So here, what I've done is I've encoded every single element. Let's write out this function. So I've encoded every single element of T. Right. What's going to happen? That's going to give us a list of encoded elements. It's going to be a list of string. Okay, so once I have a list of strings, how do I encode the actual list? Right, well, the JSON representation is going to be like element 1, element 2, element 3, element 4. So there's the way to do that in Scala is this, encoded return. And again, you don't need a return function if it's the last thing that you're putting in there. Encoded elements dot mk string dot comma, or let's put a space in there, but you can also do the thing before and the thing after. But it's fine. Let's just make it simple. Oops. Plus. There we go. So, list encoder, and we can actually do list of foo, bar, baz. Sorry. Encode. Not encoder. Encode. Oh, right. List encoder of... yes, I have to actually do... I actually have to call string here. There. Let's do show. Okay. So I actually have to tell it what kind to get. Okay. And 1, 2, 3. Oh wait, was there? Right, because that's a list encoder of int. Okay. Now, how about we just do this? Implicit class has encoder, and it's implicit that there's an encoder of t def encode is, we just use it. Oh, and we need to actually specify our element again. So we specify there is an implicit class if we have a JSON encoder on some arbitrary t, which gives us an encode function, which means that we can just encode the element. Okay, what can we do with this? List 1, 2, 3 dot encode. And I did something wrong again. Implicit. Oh, right. Excuse me. The list encoder that I defined, I did not define as implicit. Voila. And now, dot encode. Foo, bar, baz. Dot encode. Voila. Let's say I define a encoder on some arbitrary element. Let's say that I define an element called blah. And let's say blah has a value, which is of type string, case class blah. And then let's say that I define a Let's say I define a blah encoder on type blah, and that's an encoder of type blah. Right? And then let's say the way to encode that is to do, I don't know, blah, and then let's say the value. I have a blah encoder, list of blah, foo, blah, bar, blah, as, code. So I have, for free, a list encoder on anything of which I can define an individual element encoder. Just like I have here, for free, a lifter on a list of anything whose element I can define an encoder for. So this is already getting to the point where it's pretty damn powerful. Right? Because then we can incorporate that list encoder into higher level encoders. So for example, right, we have this property alias lifter, right? We've lifted a property alias, okay? And because paths is a list of string, well, we have an encoder of list of string, and we have an encoder of string, therefore we could just, guess what? We could just encode it. Lift it, in this case. Now, how about property alias? Entity has a property alias. Let's say we don't just want to create an empty list. Let's say we just want to create a property alias. Property alias dot lift. Again, it has to be lift A because property alias is a list. Oh, look at that. Property alias, which is a list of property alias, goes to the property alias lifter. The property alias lifter then lifts the list of paths, which again, it can lift into a list because there's an encoder of list. And so we have this method of generic lookups that we can just do. Let's see, this should compile. And voila. Okay, it compiles. So this is why you'll see in the real when it comes time to do the real code base. This is why the parser is organized, or excuse me, the lifter is organized this way, in order to take advantage of this kind of capability. Questions?
I don't have any.
No questions.
Yeah, I didn't have any like really pressing questions for this.
Okay. So this is, I mean, when we covered type classes, we did a lot of this stuff. So if you actually take a look at, by the way, if you actually want to look at how internally Scala does this expr thing, right? What is expr? Oh, expr just implements liftable, quoted.liftable. So internally, Scala actually has its own liftable type class, right? Implicit evidence. That's what it's called. So, okay, what I'd like to look at, because we are in Scala 3, we are doing implicit classes and implicit defs, but there's actually a different way of doing these things in Scala 3, and I want to take 5 minutes to look at it. Extension methods. Yes. So in Scala 3, this has changed. What version? Let's see, what version are we using? Are we using the latest the latest thing here? No, we're not. No, we're not. Wait, oh, hold on. No. 1 second. 1 second. Oh, we're using. Okay, now we're using this version. Okay, let's commit what we have so far. Let's commit what we have so far. Probably the 15th. Okay. What version of this?
Hey, Alex, just letting you know I'm gonna have to go
Okay.
soon.
Okay, that's fine. All right. All right. You know what? I don't want to do this now because there could be errors in the code base, and we can cover this next time. There's a slightly different way of doing this in Scala 3, and I wanted to explore that right now, but I think that we can pause on that for now. Okay. There's one other thing that I wanted to mention. That also I don't want to go into now. But the way that the parser is defined and the actual code base is different. So at the root of it, we said, what is a parser? A parser is something that transforms some expression into an abstract syntax tree, or throws some kind of an error. What I wanted in the real code base is to be a little bit more flexible. The idea is that let's say that right, we have like different kinds of parsers, right? Let's say that we have a parser that parses queries, right? So let's say that we create something called a query parser. We create something called a query parser, and that has, say, parse query. And then let's say again it's an expression. We won't define it too carefully yet. And what this thing returns also is some kind of syntax tree, because that's what everything is. Right, so let's say that we do something like that. Right? And then, or let's call this AST parse. And then let's say we have another kind of parser. Let's say we'll define this as the binary operation parser, or operation parser. Again, what this has is some other clause, like these two things. What I wanted to do is to create what you can call composable parsers. In other words, you can do something like object full parser consists of, let's say, query parser and operation parser, and a bunch of other parsers. This is a pattern that I implemented. And again, in the interest of time, I'm not going to go into this further. except for explain that this is sort of the goal behind the parser as it's implemented inside of here. So the idea is that I have all sorts of different parsers. So there's a query parser. There's a operations parser. There's a generic expressions parser, etc., etc. And they are composed together in this function here called parser library, where they're individually defined and then composed over here. The reason why this is done, and by the way, given is, you may have seen, it's implicit, given is a, it's changed to given actually. The reason why I didn't want to go into that further is because, again, it could still change because Scala 3 hasn't been released yet, which is why I'm using implicit, which is the old way of doing it. But anyway, this is the same as implicit. So the idea is that there's this ability for the user to actually create their own parser library and extend these methods and define their own parsers. So this is why it's defined in this kind of flexible, composable way. This is combine, right? So this is like, full parser equals to query parser dot combine operations parser dot combine, and then other parsers. And that's what this pattern is here. So I think we should actually call it an early evening. So this actually, again, it's defined a little bit more complicated. If you actually want to define this pattern, you'll see there's some other ceremony that I have to do in every single one of these clauses. But you guys are going to be writing basically new parsers that are then going to be composed into this big parser. Because of this additional complexity, there's this additional ceremony that's required. And the additional complexity is that if you're combining all of these, AST parse needs to go back to the composite, right? Like, what does it mean that you're combining all of these, but when inside of this guy you're calling AST parse, he doesn't know about this guy. So when you call this guy, you call this method, where does he go? So that's why there's additional complexity here that I had to add that sort of does all that. That's why there's more ceremony here. But anyway, what I'd like to leave it to you guys to do is, so we've implemented the pattern of type classes. We've implemented the pattern of type classes to our lifter, right? And we've used this pattern of type classes in our lifter. So my challenge with you guys is do the same thing to the unlifter, right? Like the unlifter is a mirror image of the lifter, and try to do something like this. Try and create an unlifter of an entity, right? And so,
I see.
So what you're going to have is something like, again, it's going to be a little bit more challenging because there's this quoted context, but again, you can create, you can do something like, oh yeah, no, that's fine. You can do something, that actually doesn't matter. Trait unlifter, right? And then you'll have trait unlifter of t. Ooh, wait, no, sorry, you can't do that. Let's just call it something else. I will actually change the name. I'm going to call this unlifter engine. I'm going to call this unlifter engine and change all of the references. So create one of these, define unlift, which is going to take an element of t. Now, not t, we're unlifting, right? In the lifter, it was t to expression of t. In the unlifter, it's the opposite. It's expression of t to t. And so in this case, for example, let's say we want a entity unlifter, right? What that's going to be is that's going to be something like implicit def entity unlifter, which is going to be a unlifter of entity equals to new unlifter of entity, def unlift of element, which is going to be an entity, which is going to be an expression of entity, returns to us an entity, which is going to be element match, and then this guy here, right? So then what you can do is that you can do something like let's say case let's say this is actually a little bit more challenging because you have to look something up in a tree, but let's say case E of type entity, and so now we know it's an entity expression. Then we can do, and again, you'll have to implement, let's say, implicit def has, implicit def class has unlifter, and then.
All right, I gotta go.
Okay, go ahead. I'll
watch the rest of this later.
Sounds good. All right, I'll just finish this up quickly. Has unlifter
Thanks.
t, that's an element of t, and then implicit unlift, let's say unlifter, which is going to be an unlifter of t, and so we're going to have unlift, which is gonna return, and excuse me, this is going to be expression of t, again, mirror image of what we had before, unlift of t, and what that thing is going to return is a t. And so what you're going to have, oh, by the way, it's unlifter dot unlift on an element. And so now we know that E is a type of entity, and we'll have E dot unlift. Let's see if that'll compile. Oh, right, I have to change. Unlifter, and it's, how do you do Control H? Not Control H. Control R? Not Control R. not Control-Shift-F. And you do replace. Unlifter engine. Engine. Na-na-na. 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 Okay. Unlifter engine. Unseal util. Quote context. Oh, wait, no, that should be fine. Class unlifter engine. Let's try to compile it. No implicit type quote context. What happened here? Unlifter engine has unlifter element of reference error. Expert of AST. Unseal util.expert does not take type parameters. Class unlifter engine. What did we do wrong? Reference error expression of T. Unseal util.expert does not take type parameters. Quote context. Oh, wait a minute. Is this, let's try fly on left. Let's try this. Okay, wait a minute. Let's try apply on left. Lifter, there we go. Has on lifter. Let's try apply on left. And there. Apply on left. Expertise QCTX is ambiguous. And oh, and then of course, right, where did we define? Ah, I know what happened. Where did we define this? We defined that here. Class unseal util. No. Implicit val QCTX. No parameter quote context found. Okay, guys. I will let you go, and I will fix this up and post this. So, yes, as the homework, once I fix this up, try to implement the type class pattern inside the unlifter, and then we'll be ready to go for next time. Have a good night. Okay, what if we don't make this implicit? Aha! So the second that we make this implicit, again, lots of things go to hell. Why? We make it private? No. Okay. So now what? So, does this compile? What if we import stuff? We can do that too. If we do that, and that. Okay. Okay. So it seems like there's something super context sensitive about this whole thing. Okay. So then, what if we define this thing? What if we define this thing in the Unlift library? Then what? Has unlifter dot unlift. Okay. So what happens if we define that there, and since we've imported all that there, we just do unlift. Okay, well, I guess when you get rid of this, I guess when you get rid of this unlift library, something overrides the context. Not sure what, but okay, fine. So implement the unlifters inside of the unlift library. That's fine. And then you could still use them out here. So anyhow, this is the pattern. This is the pattern, and so yeah, you could implement this a similar kind of pattern to be able to unlift different kinds of things. For example, identities and stuff like that. All right, so this is good. This is a good start.